Welcome back. So this is a vignette that I'm very excited about because it touches on a theme that's come up quite a bit in the course, and that is the notion of mechanism. So mechanism is a word that's in some sense it's kind of a word that's fraught, and the reason is because different fields have different norms. I guess is the simplest way to say it about what constitutes a mechanism, and I think that that's fine until we start trying to talk to each other. And then you get in this thing where you're literally kind of talking past one another because words can be tools, but they can also be weapons. And the point of words is to communicate, actually. And so what we need to do is we need to agree upon what we mean by words when we say them, and then after that we can maybe end up disagreeing. So I'm going to be concrete about this. When I was a postdoc, I worked on the subject of quasi-crystals with a guy named Chris Henley and another guy named Mike Whittam, while I was at Cornell, and it was really fun, and it was really interesting, and I was a know nothing and incompetent, and they were very generous with me, but I learned a lot from talking to those guys and interacting with them. And the quasi-crystal idea, this may seem like it's a million miles away from biology, but it's actually not. It's right in the neighborhood. So quasi-crystals, if I were to try to embody the simple statement, it is that if you look at the tiles in a bathroom floor, you can see equilateral triangles, you can see squares, you can see rectangles, you can see hexagons, but what you will not see is pentagons by themselves. And the reason is you cannot tile a floor with just pentagons. It doesn't work. And there's a whole array of things that go along with that, which then would lead to a belief, a wrong belief actually, and this is related to my previous thing on numeracy, that there could be no fivefold diffraction patterns, that you would not have crystals with orientational symmetry of the pentagon or the icosahedron. And that turned out not to be true, and actually numeracy would have told people that if they'd actually done the right calculation ahead of time. Anyway, why do I mention this? Because one of the very interesting things, in the early days, people like Paul Steinhardt and Veit Elser and Chris Henley had worked out, Dov Levine, they had worked out some interesting theoretical models that are related to Penrose, actually, and they're called Penrose tilings. And it turns out that those also have sharp diffraction patterns, and people were trying to figure out where the atoms are. Okay, that's the reason I'm bringing this up. This is not a structural biology thing. This is a physics thing. This is where I acquired my attitudes about atoms and knowing their positions. It was not in reaction to structural biology. It was in reaction to, not even in reaction, it was part of the pleasure of being part of that very tiny part of that discourse in the context of a puzzle, which happened in the 1980s, which is how did you get diffraction patterns with icosahedral symmetry? So people were trying to figure out where the atoms are. And when I was at Cornell, I gave a talk with the title like Quasi-Crystals, Where Are the Atoms? And that's because I had this brilliant collaborator, Mike Whittam, with whom I worked, and he had so many clever ideas, and we worked hard, and like I said, I really learned a lot. But then at the same time, there was this whole continuum hydrodynamic theory written down by people like Steinhardt and also by people like Whittam and others, Ramaswamy and John Toner, and I don't remember all the players. And there were these really interesting excitations known as phasons. And so I ended up giving a talk, my second talk, and maybe I think even my job talk from when I went to Brown was quasi-crystals, are there atoms? Now this was a joke, but it was really making this point, which is that mechanism is not strictly knowing where the atoms are. Now, of course, it could be true that you're a structural biologist or a biochemist, and that is your definition of a mechanism. You need to know which atom is touching which atom and which electron is getting donated to which other atom or whatever. You're allowed to have that as your rigid and sort of hardliner definition of mechanism. That's fine. And then if we have a conversation, I will know that that's what you mean by that word, and I will know that I don't share that definition. That's too restrictive for me. In other words, scientific explanation of phenomena needs to transcend just where the atoms are and what the atoms are doing. And I've already given several examples, and I'm going to give hydrodynamic examples here. But I talked about the Golden Gate Bridge. I was out there a few weeks ago, and it was the strongest I'd ever seen the wind, and I stopped in the middle, and the bridge was basically playing music. The wind was blowing so strong that different resonant frequencies were being set up, and it was singing. And there's no sense in which an atomic level description of the mechanism of the bridge singing would make particular sense. Or even if you could do it, I wouldn't want to. I would want to have a higher level description. Okay, so there's this great paper, which I really recommend that people read, by Phil Anderson, written in 1972 in Science Magazine, known as More is Different. And it's got staying power, in my opinion. This is a very deep article. And what he was up to was he was critiquing his fellow physicists. This was not aimed at anybody, really, as far as I can tell, other than his fellow physicists, and in particular, the field theorists and particle physicists who were trying to claim ownership of the word fundamental, I guess, is what I would say. And so the argument was that, there are certain phenomena that don't even exist at the level of the atoms. You need to put a bunch of atoms together to even get the phenomenon to exist. And so, he tried to make this point that, subject A is not just applied subject B. Dirac, in one of his early papers, tried to make this remark that, chemistry is nothing more now than just the solving of the Schrödinger equation or something like that. But again, I doubt that is actually going to stand the test of time as a proper mechanistic explanation of things that we see. So what I'm going to do here on the subject of mechanisms, I've already made my relatively strident remarks about, I think that the scope of mechanisms should be broader. I said earlier in the term, and I'll say it again, and this applies to both quasicrystals and to proteins, which is stating the atomic positions. That may or may not be an explanatory framework. And if one wants to be a hardliner, I could always say, well, you didn't talk about the position of the protons inside of the nuclei or something like that. It would not be a serious remark because I don't believe in that. But I could say that because it would be like a kind of a purity test, an intellectual purity test for mechanism. Well, your mechanism doesn't talk about atoms, so it's not pure. And so my comment to that is, well, your mechanism based on atoms is not pure because it doesn't talk about the protons within the nucleus. But again, I think that's silly and misguided. So here I just want to point out, this picture on the lower right is the one I guess I'm most excited about. I think I've shown it already. I love these kinds of pictures from satellites, which show these very large organized structures. This is, in this case, a wake off of an island off the coast of Baja. And on the left-hand side, I think that's from Indonesia, and you see that one's more terrifying to me because you can see that there's all this structure in the water. And again, coming back to the Golden Gate Bridge, I've been doing this game lately where I've been racing ships on my bike to the entrance to the bay, and often I'll sit out in the bay on the bridge right as they're coming under the bridge, and you can see. We're talking about giant 600, let me call them 200 meter long ships, and they are absolutely fighting a beast of a current, just a really, really scary current. These things are not something that one would describe at the level of this is where this atom is going and this is where that atom is going, or this molecule of water or whatever. They're the mechanisms that you see, the mechanism of those vortices being shed off of that island. The mechanistic explanation to me is given by the equations of fluid mechanics, and that's the starting point for the mechanism. So I wanted to comment on glycolysis, and here I'm showing you a really cool and interesting diagram. I like it because the things on the left-hand side, the molecules in red are inhibitors, the molecules in green are activators. I was excited about this in the context of allostery because you see that a molecule like phosphofructokinase, shown there, the structure as drawn by David Goodsell, it has 3 activators minimally and 4 inhibitors, and there's actually more stuff in play. But people write down equations that describe the flux through these pathways that are differential equation based, and if you were to say, well, when I tune this guy, then something else happens, I could accept as a mechanistic explanation those differential equations. Someone else might not. That's fine. That's, again, what makes the world go around. It's great that there are people that are working out the structure of these molecules, but I consider it great that there are people that are also trying to understand what's the nature of the networks. I remember a very, very cool paper on all sorts of different wiring diagrams for glycolysis, where people tried to test alternative realities and to see whether the one that we actually have is in some sense optimal. And then on the right-hand side, what I'm showing you is a statistical mechanician's view of a part of the pathway through glycolysis. In this case, the statistical mechanical behavior of the phosphofructokinase tetramer. And my point is actually just that there's many different ways to consider a problem mechanistically, and in some sense it depends on our taste. In some sense it depends on what question we're asking, what we want to know the answer to. And so if I'm doing an experiment that's a macroscopic experiment with in which I'm measuring the quantities of the various molecular players in this pathway, and I'm able to tune one of them, a mechanistic explanation at that point, to my mind, doesn't have to do necessarily with the particular atomic positions in one molecule, but it might have to do with, for example, the enzymatic rate of a given molecule compared to another, or that kind of thing. So I'm not trying to take a hardline view. I'm trying to take a generous view on mechanism, really, here. And if I sound like I'm criticizing, it's just maybe that's just the result of having been victimized by sort of this unilateral view that the only kind of mechanism is the success of the molecular biology worldview, which has been incredibly successful. A few days ago, I gave this vignette about phase separation in the worm and the temperature dependence, and I just wanted to give an alternative spin on mechanism in this case. So here's the phenomenology, which is that a particular protein is fluorescently labeled. That particular protein goes into condensates. Therefore, one can use it as a readout of the presence or absence of the condensates. They cycle the temperature, shown here on the upper left. Amazing. And so these red curves, the periodic red curves, is the temperature. These grayish curves, this is the volume of condensate as a function of time. And then on the right-hand side, I showed you that they achieved the phase diagram. But for my purposes, what I really wanted to point out is at the bottom here, next to me. And that's this equation, which is the Flory-Huggins theory that we worked out in the previous vignette. We thus introduce a binary Flory-Huggins model with the effective free energy per volume. And that word effective is really super important to my whole discussion of mechanism, because you write down an effective theory, you know that you're intentionally ignoring things. It's not naivete, it's sophistication, au contraire. And so in this case, what they're asking is Flory-Huggins an explanatory mechanistic framework for understanding their observations? And roughly speaking, that they find that the answer is yes. My last example has to do with input-output curves, and what I'm going to refer to as KT mutants. So, I've been interested in transcription factors. There's Mitch Lewis at UPenn has done beautiful structural biology on the lac repressor molecule and some of its mutants. And, each mutant has its own leakiness, its own saturation, its own dynamic range, its own EC50, which is the midpoint. That's awesome. I like the idea of saying, okay, instead of classifying a mutant by a particular site which is mutated and saying which amino acid got replaced by which other, I'd like to call these mutants in KBT units by saying this is their delta epsilon. It's a particular delta epsilon mutant. So I want to kind of just walk you through this example. We talked about the allosteric model, the MWC model, earlier in the context of ion channels, and it can also be used for thinking about allosteric transcription factors. I'm not going to belabor this. We're past the technical part of the course. But this is about mechanism. So for me, the mechanism of this particular transcription factor is these cartoons. That's the essence of the mechanism, which is that there's an inactive state and an active state. The active one is shown on the top, the inactive one is shown on the bottom. Using that model, we can basically, sorry about that. We have measurements of the fold change in gene expression, and our implementation of the mechanism, our pathetic thinking, to quote the previous vignette, is captured in the model that I show you on the left. So that's my mechanistic picture of the behavior of an allosteric transcription factor. we can fit the two unknown parameters, Ka and Ki, which are the binding constants for the active and inactive conformations, onto DNA. And then we lock them in a box once and for all. So we lock them in the safe. We will never touch those parameters again. And then we make predictions. We make predictions about what will happen when we change the DNA to protein repressor binding strength, when we change the number of repressors per cell, etc. These are parameter-free predictions. And then, as I said, they're locked. The parameters are locked in the safe, and then one can go and make the measurement. So that's fine. So I really want to acknowledge Griffin, Nathan, Stephanie, Tal, and Manuel, who worked in my group on this stuff. It's not about us. It's more about mechanism. So I want to comment on mechanism from the standpoint of hidden variables. So there's this beautiful paper by Joe Keller in which he talked about a dimensionless ratio that allows you to understand whether a coin flip will be a heads or a tails. So the idea is simple. If I throw up a coin with initial velocity v naught in a vacuum, then I know that the time that it will take to go to its apex is v naught over g. And that means the total travel time is 2 times v naught over g. If I know that the angular frequency is omega, then omega times t, the total time of the trajectory, gives me the number of spins, if you like. And so I will be able to tell whether it's heads or tails. So basically, the initial velocity, initial rotational speed, our rotational frequency, are hidden variables. If I happen to know them, this is not a random coin flip anymore. So what I'm saying is that in the context of this allosteric thing, that there's the pipetting variables, the things that we pipette, the repressor number, the IPTG concentration, the DNA binding strength, and so on. But there's actually for me, a mechanistic insight, which is that what the cell cares about is this weird combination which leads to the free energy difference between the active and the inactive conformations. It does not matter how you got there. It doesn't matter whether there's a glycine or a phenylalanine or a tryptophan or whatever at a given site. What matters is the Ka, the Ki, and the delta epsilon. And that's the thing, if you will, that the cell cares about, is those values. And that's, to my mind, the mechanism. And a proof of understanding of that mechanism is given by this data collapse where, what I'm plotting on the x-axis is that free energy difference between inactive and active, instead of the unnatural pipetters variables, which is the thing that we talked about before. So the point of this vignette was basically to argue that a general definition of mechanism, which is not patriotic to any particular sort of explanatory framework, it's not patriotic to any of them. It's not patriotic to a mathematical one, a structural one, a biochemical one, or whatever. That what we mean by mechanism is maybe a little bit more slippery.